So continuing on about probability, we need to first look at what a sample space is. A sample space can be a great way to visualize what's actually happening so we can figure out what the probability is. So for here, we want to find the sample space for each of the following. One coin is tossed. Well, if one coin is tossed, right, we have A, we could either have heads or we could have tails. And that's it. But for B, we have two coins. So the first coin is going to be heads or tails. But each coin after that, well, if the first coin is heads, the second coin could be heads or tails. And if the first coin is tails, yet again, the second coin could be heads or tails. So if we have coin C, 3 coins are tossed, we could have heads or tails for the first one. For the second one, heads or tails. And then for each of those, we could have heads or tails. So this is actually called a tree diagram. We can use this to write the sample space. So for A, we have the sample space is equal to heads, tails. For B, we have that the sample space is equal to heads, 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 tails, tails, heads, and tails, tails. And then for C, we have the sample space is heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. So this is helpful because now I can say, what's the probability I flip a coin 3 times and get 3 heads? We can figure that out using our sample space. So here's the probability of any event. Probability event is going to be the number of events over the number in the sample space. So let's, for example, say, flip 3 coins, and what's the probability we have 2 heads? Well, this is going to be equal to the amount in the sample space. So here, I flipped 3 coins. So what's in the sample space? 8. So the probability, or the number in the sample space is 8. And how many times do I get 2 heads? Well, exactly 2 heads. 1, 2, 3. I'll say exactly, because we could have 3 heads, and that's not exactly 2 heads. So 3. Right. 2 heads, 2 heads, 2 heads. So for here, for A, we have 2 coins are tossed. What is the probability that both land heads up? Well, we can go back to our sample space before, right? If we flip 2 coins, what's in the sample space? Well, the sample space is 4. So the probability of 2 heads is over 4, and how many are 2? Just 1. So 1 out of 4. For B, a card is drawn at random from a standard deck of playing cards. What is the probability that is an ace? So probability of an ace. Well, in a standard deck of cards, there are 52, and there are 4 aces. So we get 4 out of 52, or 1 out of 13. So you can kind of see the probability is actually used a lot in gambling, because if you have to make a bet about whether the first card is going to be an ace or not, well, there's a 1 out of 13 probability, so that's not great. You have better luck betting against an ace. Okay, so here we have a 12-sided dice. This is taken from the textbook, so if you look at figure 8.14, you can see it there. It's an 8-sided dice, and ignore all that stuff, right? Numbers 1 through 6 appear twice on each dice. So 12-sided dice, 1 through 6 twice on each dice. Show that these dice can be used in any game requiring 6-sided dice without changing the probabilities of the various incomes. Well, so what this means is a normal dice. So a normal die has numbers 1, 2, 3, 4, 5, and 6, correct? So the probability of any number is 1 out of 6, right? If I roll a die, what's the probability that I get a 4? Well, there's 1 4 out of the 6, so the probability is 1 out of 6. For the 12-sided, die, we have 2 opportunities out of 12, right? Because we have 2 1s, 2 2s, 2 3s, 2 4s, but we still have 1 out of 6 because it reduces. So even though it seems like now I have more 4s to get, the probability of rolling a 4 on a 12-sided die is still the same as rolling a 4 on a 1-sided die. Now, if this die were labeled 1 through 12, then it would be much different. We'd be 1 over 12. It'd be half of the probability of a normal-sided die. All right, we want to talk about mutually exclusive events. So mutually exclusive events are events that can't happen at the same time. First off, if I have any events, so let's say I have 2 events. So there's 2 events. Whoops. Let me just do this. We can think of a Venn diagram. So if I think of these events, event A, event B. So this circle over here, this is probability event A happens, probability that event B happens, and then in the middle, that is where probability of event A and event B happen. So that's the intersection. So we just say that's the intersection, A intersect B, or you could say A and B. This is A union B. This is A or B. So what's the probability of A or B happening? Well, it's a probability of A plus a probability of B minus the overlap. So, what's the probability what's the probability that the weather is going to rain can't really think of a good example here. Oh, I guess maybe a deck of cards, right? So what is the probability of, in a deck of cards, getting a face card and a heart? So probability A would be getting a face card, like a king, a jack, queen. The probability B would be getting a heart. The overlap would be king hearts because we're counting them twice, so we need to subtract that. Now, when events are mutually exclusive, it means there is no overlap. So the probability of A intersect B is equal to 0, so it's just the sum of the products. So we have probability of A and probability of B. These are 2 mutually exclusive events. So, what's the probability that tomorrow the weather is going to snow and it's going to be sunny? Well, those are mutually exclusive events. It can't snow and be sunny at the same time. If it's snowing, it means there's cloud coverage, there's no sun. All right, so here we go. One card is selected at random from a standard deck of 52 playing cards. What is the probability that the card is either a heart or a face card? So event A, I'm going to define as a heart. Event B is a face card. So either means probability of A or B. It's A union B. Well, from the last slide, we can see that that's the sum of the products, probability of A plus probability of B, minus their intersection, so the probability that both happens. Well, the probability I have a heart is 13 over 52. And the probability I have a face card is 12 over 52. There are 3 cards that are both face cards and hearts. King, jacks, queens. So that's a 3 out of 52. So this is going to be 25 or 22 out of 52. Which we can reduce to 11 over 26. So the probability of getting, so if you're playing poker and you need to get either a heart or a face card, your probability is 11 over 26. That is less than half. So if you're thinking, should you fold or should you keep playing? You should probably fold, unless you're good at bluffing. Now, independent events are events that can't both happen at the same time. And so here, independent events are events that don't impact one another. So here we can just multiply the 2 events to happen together. So for example, we have a random number generator, and it selects 3 integers from 1 to 20. What is the probability that all 3 numbers are less than or equal to 5? Well, the probability of that happening, just the one time, let's say it happened once, what's the probability? Well, out of 20, there are 5 numbers, so that's 1 out of 4. But now it happens 3 times. So the probability of this happening is just the probability of A times the probability of A times the probability of A, which is 1/4 times 1/4 times 1/4, which is equal to 1/64. Because these are completely random. Random and independent go together very nicely. If you see one, you probably see the other. The fact that it shows, let's say, 3 for the first number has no impact about it being the second one. Now, if I have a bunch of marbles in a bag, and I, for example, don't put one back in, the probability for selecting a second marble has changed. So those aren't independent. But if I do replace, put it back in, then it is independent. So here we have a poll that said approximately 13% of adults got most of the news from the internet. This is in 2009. So in a survey, 10 people were chosen at random. What's the probability that all 10 got their news from the internet? Well, just the one. Imagine you're picking just one. What's the probability of just that one? Well, it'd be 13%, so 0.13. So for all 10, we would multiply that together 13 times. Well, if we're multiplying something together, or it's not 13 times, 10 times. If we're multiplying something together 10 times, we just raise it to the 10th power. And so this is equal to, oh boy, let's make sure I count my decimals here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8 zeros there. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, about that. Well, get rid of that. It's a really small number. So that's what we want to do because they're independent. The fact that I pick one doesn't have any impact on the other. So we're going to look at some example problems like this, but make sure you know formula for independent events, and then to find the probability of two events, the union of two events, including mutually exclusive events where the intersection is 0.